Let's take a look at a few more integrals using integration by parts. So if we want to take the integral of the natural log of x dx, we're going to use our integration by parts formula. So integration, just as a reminder, integration by parts. Our formula says the integral of u dv is equal to the integral of u times v minus the integral of v du. So our steps for this were on the previous video. So we're just going to jump right in, identifying what our u and our dv should be. On the previous video, I talked about a little acronym that can also be useful in helping to pick u. And it doesn't always work, but it can give us a starting place. And I mentioned before that you can think of it as liate, or you could actually flip these two and think of it as ilate as well. So either of those two acronyms can be helpful in starting. So basically, if you have the L stands for logarithmic, so if you have a logarithmic or an inverse trig function in your integral, then that would be the first pick for you. Otherwise, go down in order. So if there's no logarithms, no inverse trig, then go to algebraic functions, trigonometric functions, exponential functions, and use those as kind of your starting spot for u to give you a place to pick u. So in this case, I see that I have a logarithmic function. So my u would be the natural log of x, and then dv is going to be everything that's left. Well, since all that's left is 1 dx, dv is just dx. Now remember, we now need to find, in order to plug into the formula, we need to find du and we need to find v. So we use differentiation to find du and we use integration to find v. So when we take the derivative of the natural log of x, du becomes 1 over x, du dx becomes 1 over x, and then we multiply both sides by dx to separate the differential. When we integrate, let me get rid of my arrows here. When I integrate, those are my little thoughts. When I integrate just, right, we're taking the integral here. When I integrate dx, I find that v is actually just x. Now, we're going to plug those into the formula. So I'm just going to rewrite. I have some notes here, so I'm just going to rewrite my problem. The natural log of x dx is equal to, so again, this was the integral of my u dv. That's going to be equal to u times v minus the integral of v du. So again, the more times we write that, the more likely we will get that formula memorized, and we definitely need that formula memorized and know how to use it. So here we get u times v. Sometimes I like to write these little arrows, like you'll see me say, okay, so we're going to take u times v, and then we're going to take v times du. So u times v, we're going to get x times the natural log of x minus the integral. Now we take v du, so x times 1 over x dx. And then what we've done, and our whole purpose here of doing integration by parts, is to try to get to an integral that is easier to work with. And notice when I have x times 1 over x, that just becomes 1 dx. And the integral of 1 dx is simply x. So x, natural log of x. Now, we also, it's an indefinite integral, so we also have an integration constant, so we have plus c. And there we go. I guess we could write that. Sorry, I just noticed there's a common factor, so if we would prefer to write it, either of those two forms would be acceptable. And what's interesting is here is one of those integrals that we might want to put into our useful integrals table. It's certainly one we might see again. We could do integration by parts again if we came across it. But this is one, the integral of the natural log of x. It's a pretty basic function, and we didn't know what its antiderivative or what its integral was before we used integration by parts. All right, let's go to another one. Okay, let's take a look at another example. So we've got the integral of x cubed e to the negative 2x dx. And again, remember, we're using our integration by parts formula. So our integral of u dv is equal to u times v minus the integral of v du. And just as a little note, we can pick u, kind of keep this off to the side. We can pick u using that little acronym as mentioned on the last example, liate or ilate if you switch the I and the L. So as we're thinking about what should my u be here, and I look at this and I see an x cubed. So there's no logarithms, there's no inverse trig, but this A stands for algebraic, And algebraic functions are functions that are polynomials, rational functions, root functions, anything of that nature. So in this case, I see that I have the x cubed, so that's going to be a good candidate for my u, or let's start with that x cubed as my u and see if it works out. My dv will be everything that's left, so e to the negative 2x dx. Now, when I take the derivative, du becomes 3x squared dx, and when I integrate, v is going to become minus 1/2 e to the negative 2x. Now, we're going to go to the integration by parts formula, so we need u times v minus v du. So I'm going to go ahead and come down here, rewrite my original integral, x cubed e to the negative 2x dx, and that's going to be equal to u times v, so that's a minus 1/2 x cubed e to the negative 2x minus the integral. Now we're going to multiply minus 1/2 e to the 2x times x squared, 3x squared. So we end up with a minus 3/2 x squared e to the negative 2x dx. And of course that minus and that minus would cancel and become a plus. We would be adding that integral. So take a look at that. We have gotten to a place where we have a simpler integral to work with because we no longer have x cubed, we now have x squared, but it is still a product and it is still an integral that I'm going to need to apply integration by parts to. So this is a chance to do repeated integration by parts. So we're going to do a little repeated integration by parts. So let's get rid of my highlight and let's go for round 2. So this was round 1. Let's go for round 2. So we're focusing on this integral right here. The 3/2 can actually come out of the integral and come to the front. So I'm going to go ahead and put the 3/2 in front and re-highlight because my highlight disappeared. And take a look at that integral. So on that integral, my u is now going to be x squared. So we haven't reduced down that polynomial, but it has gotten smaller. And my dv will be everything that's left. So we get e to the negative 2x dx. So then my du is 2x dx. And my v is negative 1/2 e to the negative 2x. And we're going to go ahead and go back to that integration by parts formula. That integral that I have highlighted will become u times v minus v du. So I'm going to rewrite where we started at, keep everything in order. We got a lot of terms going on here and a lot of integration. So let's keep everything in order. So the integral I started at, the first term, which came out of that first integration by parts, negative 1/2 x cubed e to the negative 2x. Plus, now we have 3/2 times, and now the integral that we just calculated, okay, through integration by parts. So we're going to have x squared times minus 1/2, so that's minus 1/2 x squared e to the negative 2x. And then we have minus the integral. Now we have minus 1/2 times 2x, so that is a minus 2 over 2, which will become 1, x e to the negative 2x dx. Now, of course, these become plus, and that 2 over 2 becomes a 1. So I'm going to go ahead and just erase it because it becomes 1 and write this as the integral of x e to the negative 2x. Now I'm going to go one more line of simplification because we need to distribute the 3/2 to both of these terms. So I'm going to go ahead and do that. So I get minus 1/2 x cubed e to the negative 2x minus 3/2 times negative 1/2 is a minus 3/4 x squared e to the negative 2x plus 3/2 times the integral of x e to the negative 2x dx. Okay, we're getting closer. We're getting closer and closer at each step. Let's get it all on the board. At each step, but I do want you to notice that this integral, we need to repeat integration by parts again because we have reduced down that x cubed down to just an x on this integral, but it has not gone away. So we need to, again, repeated integration by parts again. We're going to go again. We're going to go for round 3. So for round 3, our u is going to be x, and our dv is everything that's left, the exponential e to the negative 2x dx. We take the derivative. Du is going to become 1 dx, or just dx, and we integrate. V is minus 1/2 e to the negative 2x, and we go ahead and put that back in using our integration by parts formula, And again, I'm going to go back to the original. X cubed e to the negative 2x dx is now equal to, I'm going to carry these two terms down from above, minus 1 half x cubed e to the minus 2x minus 3/4 x squared e to the negative 2x, plus this time we have 3 halves times, and now the integral is going to become u times v. So we get minus 1 half x e to the negative 2x minus the integral of v times du. So that becomes minus 1 half e to the negative 2x dx. So let's go ahead and continue. We're going to distribute this 3 halves. We're getting closer and closer. I do notice right here this minus and this minus, so that becomes a plus, and we'll distribute that 3 halves. And we're actually done using integration by parts. I'm rewriting this while trying to talk, but if you notice down here at the end, that integral is now one we can do without integration by parts. So we had repeated integration by parts, but we finally got ourselves to a spot where I don't need to use integration by parts. So I'm going to distribute that 3 halves. I'm going to trying to think ahead of where I'm actually writing. So this becomes a minus 3/4 x e to the negative 2x, and then we have plus 3/4 times the integral. I pulled the 1 half out and multiplied it by 3 halves, e to the negative 2x dx. Okay, so now we can finally integrate. This is just the integral of e to the negative 2x. So we have 3/4 times a negative 1 half e to the negative 2x. Now at each stage we had an integration constant. I didn't write them as we were going, but we will have a plus c here at the end. I'm going to go ahead and actually rewrite it on the very next line. So all that stuff is just going to come down, and we get minus 1 half x cubed e to the negative 2x minus 3/4 x squared e to the negative 2x minus a 3/4 x e to the negative 2x minus a 3/8 e to the negative 2x plus c. And if we really wanted to clean it up, we could pull out a common factor of, looks like we could pull out an e to the negative 2x. And even a 1/8 if we really wanted to. I'm going to leave it as is. We could definitely simplify a little bit if we wanted to, but I want to talk about, this is a nice one to illustrate a technique called tabular integration by parts. And I want to show it how we could have organized our work a little bit differently. We could have organized our work in a table here, but we don't have to. We can do repeated integration by parts just like I did here. I'm going to try to get it all on the screen. Up here you can see the end of another problem, but trying to get that all on the screen at the same time, right? Had to get kind of small because we had to do repeated integration by parts here. We had to do it 3 times, but we did get to our answer. But the process, that repeated process that we did, was the same every time. Each time we picked our u to be the polynomial and our dv to be the exponential function. And so I want to just show you a way to organize it that is called tabular integration by parts. I'm going to show it to you on this particular example. It can be used and manipulated. The process I'm going to show you can be used and manipulated even if our u doesn't end up zeroing out. But I won't go into too much. If you like this process and you want to play around with it and utilize it in other integration by parts examples, go for it. I will show it to you on this one, and then you can expand if you really like it. So I'm just going to rewrite the problem. What was it? I think it was x cubed e to the negative 2x. Okay, so let's start this problem over again. And tabular integration by parts is handy when we have a product of something like a polynomial times another function, where we know that if we pick u to be the polynomial through repeated integration by parts, through repeated derivatives, that u is going to go to 0. So if we see something of that nature, we can use this process called tabular integration. And I'm going to draw the table. It's just a way to organize. So it's an organization method for integration by parts. We create a table, and down the first column, we put u. And down the second column, we put dv. So on the very first line, just like we would normally do, this is our first pick of u and dv. So we pick x cubed and we pick e to the negative 2x. So there's our u and our dv. Now, down the first column, we are going to repeatedly differentiate. So down the u column, because when we take u, the first step of integration by parts is to take the derivative. So down the u column, we are going to be using repeated differentiation. So we take x cubed and we take the derivative, 3x squared. Then we take the derivative again, we get 6x. Then we take the derivative again, we get 6. Then we take the derivative again, and we get 0. This is one case, as I mentioned, where tabular integration is especially nice if you get a 0 in this first column. Now, it can be used in other forms, but for sure when our u zeroes out because it's a polynomial, so through repeated differentiation if it zeroes out. Now, down the other column, so down this column, right, we were doing differentiation. Now down this column, we're going to do repeated integration because when we use integration by parts, we take the derivative of u to get du, and we take the integral of dv to get v. So down this column, we're going to do repeated integration. So we take the integral of e to the negative 2x, and we get negative 1/2 e to the negative 2x. And then we repeat it, and we get positive 1/4 e to the negative 2x. And then we repeat it, negative 1/8 e to the negative 2x. And then we repeat it. And we repeat it until we get into a line with where we want to stop on the left column. So we repeat that, and we now get positive 1/16 e to the negative 2x. Now that we filled in our column, the way we go from this tabular organization into our solution for integration by parts is we actually go down on a diagonal. So the first product, the first u times v is right here. X cubed times negative 1/2 e to the negative 2x. Now the second u times v is right here. But here's the thing. Remember in integration by parts, the integral of u dv equals u times v minus the integral of v du. In integration by parts, on the second integral, we are subtracting the result. And so if we're subtracting another u times v, we have to account for that in our tabular integration. So in tabular integration, along each of these rows, we need to change the sign. So the first u times v, we're adding. The second u times v, we will be subtracting, and then adding, and then subtracting, and then adding, because we're adding the first one, and then we're subtracting the second one, and then on the third one, we're subtracting a negative, so that becomes an addition again. So we put those down on the columns. So we remember for our first u times v, it's going to be plus x cubed times negative 1/2 e to negative 1/2 e to the negative 2x. So up here, as I'm going to go ahead, I need some space, so I'm going to go ahead and move that all the way over. So as I'm writing this, my first u times v is a minus 1/2 x cubed e to the negative 2x. And then my next u times v is going to come from right there. So it's a minus 3x squared times 1/4 e to the negative 2x. So that becomes minus 3/4 x squared e to the negative 2x. And then my next u times v comes from this diagonal, u times v, and it ends up being 6x times negative 1/8 e to the x, so that becomes a minus, since it's 6/8, that becomes a minus 3/4 x e to the negative 2x. And then my next one comes off of this diagonal, 6 times 1/16 e to the negative 2x, and we're subtracting at that point because of that pattern of subtracting the integral of v du. So now we get 6 negative 6 times 1/16 becomes 3/8 e to the negative 2x, and then we have a plus c. Now, I don't have to go any further. This is why when it zeroes out, it's perfect, because everything that followed would have a 0 times whatever the integral of our dv is. So I don't have to go any further. As soon as that 0 zeroes out, that is the end of my table. So we know that our table ended right there. If we did not get a 0, there are ways that you can manipulate, because across this line right here, this would be the integral of v du from the line above it. So you can pop out of tabular integration with an integral here rather than where we ended. We ended with the full, we actually had the integral of that last term, but you can manipulate it, you can play around with it. And so tabular integration can be really fun. It can be a fun way to organize your work. You just have to remember that your u times v's are coming off the diagonal, and adjust for those signs as I did there with the plus minus, plus minus, plus minus. Okay, so I'm trying to get this original problem back on the board here. I just wanted to notice right here that we have the exact same answer, and we just organized our work in a table rather than through that repeated integration by parts. So, pick what you like. If you don't mind just following it through and being careful with your distribution and your repeated integration by parts, then you can do it as I did at the beginning of this example. If you like to organize your work in a table, if the table helps you to keep things organized and keep track of signs, then use the table for repeated integration by parts. All right, so we'll definitely practice more, and if you want to see more with tabular integration, be happy to look at more problems where we can utilize it in the problem session this week.